We're going to finish our discussion on Chapter 8 on mid-latitude cyclones. Now, mid-latitude cyclone is a large-scale storm that forms frequently over the continents. It's the source of the majority of our winter weather across the United States. Now, you have the mid-latitude cyclone starts off as something called a polar front, which is a semi-continuous boundary, the front separating cold polar air with the more moderate mid-latitude air. And then you get distortions in that polar front, creating a wave form, or what we call a wave cyclone, and then develops into what we call the mid-latitude cyclone. And that mid-latitude cyclone will move along the polar front just like a wave would move across the water. Now, let's talk a little bit more about the formation of a mid-latitude cyclone. So here we are in the left-hand figure. We have a regular stationary front. In fact, this is our polar front, where you have cold air off to the north and warmer air to the south. But what you have, remember that with a stationary front, you have winds that are moving in opposite directions on either side of the front. And so the front in between is going to be sheared or curled right in between those two winds. And so, since it starts to curl, in that case counterclockwise, which is what always happens here in the northern hemisphere, you start to form a low pressure system. And then since the air is now rotating, no longer is your front stationary, but you form on the left-hand side a cold front where the cold air is now overtaking the warm air, and then on the right side a warm front where the warm air is overtaking the cold. This is what we call our frontal wave. It's the first stage of the life of a mid-latitude cyclone. As this continues to form, the cold front will start to approach and catch up with the warm front, leaving this kind of a pie shape in the middle. This is what we call a warm sector. And once we reach that point, we've got what we call an open wave. Now, this is going to continue for a while until that cold front actually catches up with the warm front. Now, remember from our previous video on fronts that the moment when a cold front catches up to a warm front, you get an occluded front. So this is the initial occlusion stage. It is now a fully mature mid-latitude cyclone at this point. Now, I have to point out that at this stage, this is often when we get a lot of our most serious weather, in this warm sector of the open wave or in the warm sector of your initial occlusion or your mature cyclone. That's often where we can see tornadoes, but we'll see more about tornadoes in Chapter 10. But yes, that is the area where we would often see those types of storms. Now, as the cold front continues to overtake the warm front, your occlusion is going to grow, and you're going to have what's called an advanced occlusion. And then eventually, this advanced occlusion is going to advance so far that it kind of pinches off the front from the low pressure itself, and so you get yourself what we call a cut-off low, because the low pressure is now cut off from the front itself, and the front returns back to its normal polar front situation. Now, it is possible for multiple of these cyclones to form and move along the polar front in a wave-like manner. You can have multiple of these mid-latitude cyclones. Here's a good example of one where we have a beginning stage where you start getting your wave forming here, early stage, and then here where you get an open stage. Coming back here, remember they're frontal wave and open wave. There we go. So here's your frontal wave Then you have an open wave with a warm sector right in here. And then later on the very same front, we have an advanced occlusion for a third mid-latitude cyclone, all along the same polar front. And one point it's on the slide, but I didn't mention it. When this happens, we call them a family of cyclones. Now, what can actually start off this low pressure, the frontal wave? What can start the frontal wave? There are a number of things that can happen to do that, and whenever this happens, we call it cyclogenesis, the formation of a cyclone. Perhaps the most common is what we call a lee-side low. So you've got your polar front bringing air across a mountain range, but then as the air moves to the leeward side of a mountain, that's going to form a low pressure within that polar front. And then once you have that low pressure, you've got yourself a frontal wave. So this is the most common form of cyclogenesis. Here are different very common cyclogenesis patterns. The one that we just saw would describe the Alberta Clipper and the Colorado Low, where you get those forming on the lee side of mountain ranges. Also the Hatteras Low on the lee side of the Appalachian Mountains. Another way that can form is just low pressures forming in the Gulf of Alaska or in the Gulf of Mexico. These are all very common mid-latitude cyclone cyclogenesis formations. Now here's an example of a Hatteras low. Now this is very important because of the Hatteras low, we get a very commonly known formation that we know as the nor'easter. Well, what's happening? You have cold air overtaking warm air, which is overtaking colder air, so you've got yourself an occlusion. But the air is moving in a counterclockwise direction around a low pressure system. And because it's counterclockwise, that means that over the northeast states, when you have this Hatteras low in this position, winds are going to be coming from the northeast, bringing cold, humid air from the North Atlantic over the states, brings a lot of rain at the least. Heavy snowfall is very common with a nor'easter. Now, just like cyclogenesis can form cyclones, cyclogenesis also describes the formation of anticyclones, that is, high pressure systems with clockwise moving air. Often brings heat waves into regions. So this is also very common to see. Now, we need to talk about the development of mid-latitude cyclone. There are some cases where a mid-latitude cyclone can start and then strengthen, and other cases where the mid-latitude cyclone will start and then weaken. This case here, we have a weakening situation. Why? Well, with our low pressure system, we have air spiraling inward, so you have air converging, moving into the central region at the surface. And then also likewise, if you have a low pressure aloft, then you're going to have air converging aloft as well. So you've got a net gain of air, which is going to do what to your air pressure? You're going to have more air, so your air pressure will increase, the low will weaken, therefore you have a weaker mid-latitude cyclone. Now for an anticyclone with a high pressure, exactly the same thing. You have a high pressure air moving clockwise and outward, both at the surface and aloft. And so you're going to have a net loss of air, your high pressure is going to weaken, and your anticyclone weakens as a result. So really what it comes down to is not what's happening at the surface, but what's happening aloft. This is the key to whether a mid-latitude cyclone will weaken or strengthen. In this case, it will weaken, but let me show you now a case where it will strengthen. So again, we have our low pressure system, which we just saw has converging air moving towards the center. But if aloft you're losing more air than what you're gaining at the surface, you're going to have a net loss of air pressure. Your cyclone will strengthen. This will happen best when you have a trough. Here is your low pressure trough aloft. Then what's happening with your jet stream is the jet stream is moving along between these two isobars. Notice that the isobars are getting closer together. That means your air is actually converging as it reaches the base of the trough. So you are going to have faster winds, extremely fast winds here at the base of the trough. But then after you pass the base of the trough, notice that your isobars actually spread apart. You're going to have diverging air. The air is going to move away from each other, and you're going to have slower winds above that low pressure system. Okay, the key to this is this divergence. Diverging means the air moves away from itself. The air separates, meaning air is moving away, therefore there is a loss of air mass in this column above the low pressure system. So even though you're gaining more, air is moving in towards the center at the low, air is moving away aloft, and if the divergence is stronger than the convergence at the surface, then you're going to have a net loss of air. Your low pressure strengthens because of this. And then we could go through and do exactly the same thing talking about the anticyclone or the high pressure on the converging side of the trough. And you would find the same situation there. So the bottom line, when the divergence is stronger than the convergence at the surface, then more air is taken out of the top, then your surface pressure is going to drop, and your mid-latitude cyclone is then going to strengthen, and you're going to move to more advanced stages. You're going to move to the open wave, and then to the initial occlusion, a mature mid-latitude cyclone. And all of that is because of the upper air support, in other words, the jet stream, which causes that divergence. So I use that term upper air support. When we talk about upper air support, that's just talking about the overall effect of the upper level wave of the jet stream, basically. What is the role of the jet stream? Well, the polar jet stream removes that air from the surface cyclone and supplies air to the surface anticyclone. It's this jet stream itself that is causing the convergence or the divergence in that trough. So here's another view looking at the life of a mid-latitude cyclone with the upper air support above it. On the left, you see the polar front before anything even happens, before the initial frontal wave. And you can see the air above, aloft, not a whole lot is going on. But once you can form this low pressure system in the second figure, it will also trigger the start of a trough aloft. Now, if that trough is positioned just a little bit to the left of your low pressure system, then that sets you up for divergence directly above the low pressure system, which means your low pressure is going to strengthen and you're going to get yourself a very strong and powerful mid-latitude cyclone. Now, the final figure, look here, we've got ourselves an advanced occlusion. We're getting close to the point where we have a cutoff low. Well, aloft, what that does is that creates another low pressure system directly above the the fronts, that is a cutoff low aloft. That's not a huge important point, but I just wanted to explain what this low pressure here is. It is a cutoff low in the upper atmosphere. This is also very common to see with a mid-latitude cyclone. What you need to understand is this second figure, the relationship between the surface and the air aloft, as well as this stage, the advanced occlusion of the mid-latitude cyclone.